So, welcome to the deep dive. And today we have a mission for you. We really want to radically shift how you measure the true power of AI.
Yeah, we need to completely reframe the conversation.
Right. Because, I mean, if you want to know who is actually winning the AI race right now, you have to stop counting their GPUs. Stop looking at the benchmark scores of the latest language models.
Exactly. You should actually be looking at like a local zoning board meeting in a small town in Virginia.
Yeah, or like a water rights dispute out in the
Oh,
Pacific Northwest.
yeah.
Because the ultimate bottleneck to artificial intelligence, it isn't silicon anymore. It's the speed of concrete and water pipes and, local bureaucracy.
It really is. The whole industry operated on this brute force model for years. It was just all about raw accumulation, hoarding chips.
But the sources we're digging into today, and we have a really fascinating stack of analytical frameworks for this deep dive, they show a massive transition. We're looking at the GOA-53 infrastructure thesis, the LMOS operational models, and this really interesting membrane contact phase model.
Yeah, and all of these point to the same profound shift. AI data centers are no longer just these passive facilities that blindly draw power from the grid. They're being forced to evolve into what's being called a flexible load operating system.
Right, a flexible load OS. So let me just ask you the core question right off the bat. Why is it that, in the AI era, we can no longer understand competition just by looking at who has the biggest, fastest computing capacity?
Well, to answer that, you have to look at the physical wall the industry just violently crashed into. The GOA-53 thesis breaks this down into three distinct phases of AI competition.
Okay, so what was phase one?
Phase one was just capacity. That was the mad scramble, right?
Yeah,
The gold rush to buy hundreds of thousands of AI chips.
right. Whoever had the most GPUs won.
Exactly. But once everyone had the chips, we entered phase two, which was connection. Because it became painfully obvious that having the processors meant absolutely nothing if you couldn't get a utility company to drop a massive high-voltage substation onto your property.
Oh, yeah. I mean, the queue to connect to the grid in places like Northern Virginia or London, it went from like months to literally years.
Years, yeah. But even that phase is ending now. The thesis argues we're actively entering phase three, which is flexibility.
Flexibility. So wait, even if you secure the grid connection, that's not enough.
No, because the grid itself is incredibly volatile. You might have the chips and the shiny new substation, but if a summer heat wave causes power prices to spike by 1,000%, or local regulations suddenly mandate water conservation, your multi-billion-dollar facility just sits there, idle.
Wow. So high-performance GPUs are totally useless if you literally aren't allowed to turn them on.
Exactly. And the structural concept driving this friction is called velocity mismatch, or speed and shear.
Speed and shear. Okay, unpack that for us.
So you have a fundamental collision between two totally different worlds. The digital models of AI, finance, cloud computing, they all operate on high-speed capital cycles.
Right.
They update and demand new resources in a matter of months or financial quarters.
Right. It's all instant. But the physical world, like a power plant, does not move in financial quarters.
Not at all. I mean, a nuclear power plant takes a decade to build. A high-voltage transmission line might face 5 years of environmental reviews before you even break ground.
So it's like buying the world's absolute fastest sports car, the raw AI capacity, and then realizing you live in a city with perpetual gridlock and endless red lights.
That's a perfect analogy. You have a high-speed digital OS dragging violently against a low-speed physical resource, and that friction is absolute. You can't just, write a software patch to make concrete cure faster.
You really can't. But let me push back on that a little bit. If I'm one of these trillion-dollar tech behemoths, I have effectively infinite capital. Why do I care about the local utility speed limit?
You mean why not just build your own power?
Exactly. Why not simply bypass the public grid entirely? Just buy a fleet of small modular nuclear reactors, build a massive private solar farm, and become your own private island of power. Doesn't raw computing capacity and independent power trump the need to be flexible?
Well, see, that is the instinct of every software engineer who encounters physical limits. Just build a proprietary workaround. But even a $3 trillion market cap cannot buy an exemption from physical reality.
What do you mean? They can afford a nuclear plant?
Sure, they can afford it. But suppose you build your own nuclear plant or solar farm. You are still embedded in a physical ecosystem. A gigawatt data center requires millions of gallons of water for cooling, It requires thousands of acres of land.
Oh, right. It's not just electricity.
Exactly. It requires massive political goodwill to permit the thermal exhaust. If your huge inflexible power load drains the regional aquifer, or if your cooling towers create local microclimates, the local government is going to shut you down, regardless of where your electrons are coming from.
So building your own power supply doesn't give you independence. It just changes the nature of your dependency.
Precisely. Competitiveness is no longer defined by how much power you can hoard. It's defined by your ability to keep computing under severe real-world constraints without breaking the physical and social systems around you.
Okay, that makes total sense. So that brings us to the actual art of the shift, right? The engineering of this flexible load OS. Because we are talking about facilities that consume as much electricity as a medium-sized city.
Oh, easily.
You can't just put a gigawatt data center to sleep, like closing a laptop when the grid gets busy. The thermal mass of the cooling systems alone is insane. So how do you flex something that massive?
Well, they're completely redesigning the software architecture to treat computational weight as a liquid asset, and they're doing this across 4 different dimensions.
Okay, let's go through those. What's the first dimension?
The first is temporal. Shifting through time, AI companies are separating their workloads. Heavy, non-urgent tasks like training the next generation of a massive language model, those are being scheduled entirely around the wholesale electricity market.
Oh, wow.
Yeah.
So they are essentially checkpointing the model's progress, pausing tens of thousands of GPUs, and just waiting for the middle of the night when, like, wind power is surging and grid demand drops.
Exactly. The orchestrator software monitors real-time power pricing APIs. When the price of power drops below a certain cent per kilowatt hour threshold, the cluster spins up.
And when morning comes and the city wakes up, power gets expensive again.
The cluster saves its state and throttles back down. It's incredible.
So time is the first dimension. What's the second?
Geographical shifting. This is where the physics get really interesting. If the grid in Texas is congested because of a sudden winter storm, the software dynamically migrates that computational workload to a data center in, say, Scandinavia, where hydropower is plentiful and cheap right now.
It sounds like a giant game of computational Tetris. But surely there are limits to that, right? Not every AI task is flexible. Like if I ask an AI question on my phone right now, I don't want the answer tomorrow just because electricity is cheaper then.
Exactly. And that introduces a severe boundary condition, which is the third dimension, priority. You can't shift everything globally.
Right, because of the speed of light in glass. Fiber optic cables have a refractive index that slows light down by about 30% compared to a vacuum. So a round-trip data packet from New York to Tokyo takes, what, roughly 130 milliseconds?
Yep, about that.
Yeah.
And if you're routing an autonomous vehicle's object detection or a high-frequency trading algorithm, 130 milliseconds is catastrophic.
They'll crash the car.
Right. So that physical limit forces companies to divide their operations into hard and soft loads. The autonomous driving inference, the live chatbot prompt, those are hard loads.
They keep me delayed.
No, they are hyperlocal, low latency, and absolutely rigid. They must be processed immediately on the closest available server. But model training and massive data sorting, those are soft loads. They can tolerate latency.
So the ultimate competitive edge is designing an orchestrator that can instantly triage millions of tasks per second, routing the soft loads globally to chase cheap power while reserving the expensive, constrained local power strictly for the hard loads.
Exactly. It's drawing the exact boundary between what is rigid and what is fluid. And that requires an unbelievable level of coordination, which sets up the fourth dimension, institutional shifting.
Institutional. So this moves beyond just software routing and gets into, like, financial contracts.
Yes. Utilities are actually starting to utilize these data centers as massive shock absorbers for the grid through demand response contracts.
How does that work in practice?
Well, grid operators manage frequency 60 Hz in the U.S. If demand suddenly outstrips supply, that frequency drops and the whole grid can collapse. Historically, utilities kept fossil fuel peaker plants idling, just ready to spin up and add power to stabilize it.
Right, burning gas just in case.
Yeah. But now, instead of adding power to the grid, the utility pays the data center to instantly drop its soft loads.
Oh, that's wild. So the data center agrees to be the first to slow down during peak hours, and in exchange, they get favorable connection terms. They essentially sell a virtual power plant service back to the utility.
Exactly. Dropping 200 megawatts of demand in a fraction of a second mathematically does the exact same thing for the grid as injecting 200 megawatts of supply.
So they are literally turning their flexibility into a financial instrument.
They are. But this constant reshuffling of power brings us to a really critical concept in our sources called the life membrane.
Right, because this load shifting, these demand response events, the localized water consumption, it's not happening in some abstract cloud. It's happening in our backyards.
Yeah, urban planners in the LMOS framework refer to this friction as OS compatibility errors. We have this hyper-efficient AI system attempting to interface with the legacy OS of a local municipality.
And for a long time, cities just operated on a simple heuristic, right? Attract data centers for the tax revenue and the construction jobs.
That used to be the math. But the scale of AI has altered that entirely. A single new AI campus might require the local utility to string 50 miles of new high-voltage transmission lines.
And the people paying for those upgrades are often the local residential ratepayers, the everyday people living there.
Exactly. And that's the life membrane. It's the protective boundary of everyday civilian existence. Your water table levels, baseline electricity rates, noise pollution from cooling fans, the aesthetic degradation of heavy infrastructure.
So the structural tension here is that the benefits of a new AI model are distributed globally
Yeah.
to anyone with an internet connection, but the physical friction of running it is absorbed entirely by that local life membrane.
Yes, the friction sinks entirely into specific local regions.
It makes me think of hosting a massive, wealthy music festival in a small, quiet, rural town.
Oh, that's a great way to look at it.
Like the town's local government wants the revenue injection, but the festival operates on an entirely different scale. It needs three-phase power, hundreds of thousands of gallons of water. It creates massive traffic.
And if the town's OS doesn't force the festival's OS into compliance?
The festival will accidentally drain the municipal reservoir and destroy the roads. They have to set strict conditions like curfews and water limits so it doesn't destroy daily life.
Exactly. And that's what's happening now. Cities are no longer asking, do we accept AI? The negotiation is about designing conditions for coordination.
Right. Like, under what conditions can this AI load synchronize with our infrastructure without tearing the life membrane?
They're demanding that AI companies finance their own grid upgrades, utilize closed-loop water systems so they don't evaporate local water, and guarantee they won't trigger rolling brownouts. The AI systems have to prove their flexibility at the local regulatory level.
And that local friction really scales up into this fascinating theoretical framework from our sources, the membrane contact phase model, or MCP v1.2.
Yeah, the MCP framework is incredible because it looks past the immediate engineering challenges and analyzes what this all means for the stability of complex human systems overall.
And it really challenges a deeply ingrained assumption we have in the tech industry regarding efficiency, doesn't it?
It does. I mean, in software and business engineering, we treat 100% utilization and zero waste as the holy grail. Perfect efficiency.
But the MCP framework introduces this critical distinction between rigid efficiency and fluid stability.
Right. A perfectly efficient, highly synchronized system that operates constantly at maximum capacity and cannot shift or flex is actually incredibly dangerous in the physical world.
Really?
Yeah.
Why is perfect efficiency dangerous? We're always taught that's the goal.
Because it leads to what the model calls chronic depolarization. It's a state of chronic fatigue. Think of a regional power grid where the AI data centers demand their maximum power draw 24 hours a day, perfectly optimizing their capital expenditure.
So they're getting their money's worth out of the chips.
Yes, but they leave zero spinning reserve on the grid. There is no reactive power margin left. So a minor disruption like a transformer blowing out or a sudden heat wave dropping the efficiency of solar panels has nowhere to go.
Oh, I see. The system is zero slack.
Exactly. The lack of redundancy means that minor localized inflammation instantly cascades into a catastrophic system failure. The grid collapses because it was too perfectly optimized. It lacked the capacity to maintain fluctuations.
It's like the clutch in a manual transmission car.
Oh, how so?
Well, if you bolt the engine directly to the wheels with perfect rigid efficiency, the moment the wheels hit a massive rock and stop turning, the engine violently stalls and the internal components shatter.
Right, the force has nowhere to go.
Exactly. But the clutch introduces intentional slack. It's literally designed to slip. That slipping is technically all loss of efficiency, but it allows the engine to keep running while the wheels navigate the obstacle.
That is exactly it. That intentional slippage is what the MCP framework calls civilization fluidity capacity. True stability in an era of massive computational demand isn't measured by unyielding growth or zero friction.
So what is it measured by?
It's measured by the system's recovery capacity, its ability to voluntarily slip, to shift, cool down and redesign itself under pressure rather than forcing the physical world to break to accommodate it.
Wow. So the companies that win won't be the ones who build the most rigid, bulletproof concrete bunkers. They will be the ones who build the best clutches.
Precisely. Which leads us to the final operational protocol detailed in our sources. LMOS v2.0. This is a framework for how we as observers should actually process these massive infrastructure shifts without getting totally overwhelmed.
Because, I mean, let's be honest, the public discourse around AI and the power grid is incredibly polarized right now.
Oh, it's extreme.
Every headline either claims that AI will single-handedly solve nuclear fusion tomorrow and bring post-scarcity energy, or that it's this parasitic force that's going to boil the oceans and crash the electrical grid by the end of the decade.
And the LMOS framework identifies that polarization as a failure of cognitive cooling. The media and financial cycles move exponentially faster than our human ability to digest structural changes.
So when we face extreme complexity, our minds just default to rigid binary narratives, utopian salvation or apocalyptic collapse.
Right. We adopt the same rigid efficiency in our thinking that causes grids to fail. We eliminate the nuance because nuance requires cognitive energy. So how do we actually observe this shift without getting caught in those fixed narratives? What does LMOS v2.0 suggest?
The protocol advocates for maintaining phase fluidity in our own analysis. Instead of locking onto an extreme outcome, we need to observe the gradients.
The gradients. Where is the structural tension, right?
Exactly. Who holds the negotiating leverage between a hyperscaler CEO and the mayor of a water-constrained city in Arizona?
So you stop looking at the press releases about teraflops and you start looking at the compromises.
Yes. When a data center agrees to delay its construction by 2 years to fund a new substation, you are observing the slow physical layer actively pushing back against the fast digital layer.
The gradient is the friction point where the digital world is forced to yield to the physical world.
By tracking those compromises, the zoning board minutes, the utility rate cases, the demand response pricing, you map the actual trajectory of the technology rather than the marketing hype. So you don't need to panic about an AI energy crisis, and you don't need to buy into the hype that AI will solve all our physical constraints tomorrow. You just need to watch how these systems are learning to negotiate with each other.
It's a profound process of forced synchronization.
Let's pull all of these threads together for you. We began by asking why raw computing capacity is no longer the simple math problem of who has the most chips.
Right, it's evolved.
Through the lens of these structural models, we've seen that the competition has fundamentally transformed from a hardware accumulation race into a complex physical design challenge. The velocity mismatch between high-speed AI cycles and low-speed physical infrastructure has made brute force expansion a total liability.
The new baseline for survival is the flexible load operating system.
The winners will be the organizations that can seamlessly orchestrate their power demands across time and geography, distinguishing between hard inferences and soft training loads. They're the ones turning their massive energy footprints into financial shock absorbers for the grid, negotiating the friction at the edge of the local life membrane, and prioritizing fluid stability over rigid efficiency.
The capacity to adapt to physical constraints has become infinitely more valuable than the capacity to just compute.
So the next time you read a headline announcing a breakthrough in GPU architecture or a massive new data center breaking ground, look past the silicon. Don't just ask, how fast is it, or what's the peak power draw? Ask how intelligently that system can slip its clutch. Ask how well it bends to the slow, messy reality of the physical world.
But, there is a corollary to that adaptability, which is perhaps the most important provocative question moving forward.
Ooh, what's that?
Well, currently we are watching AI software contort itself to fit the limitations of our legacy power grids and our 20th century urban planning. But flexibility is a two-way street. Once these highly integrated, autonomous AI systems completely master the constraints of our infrastructure, what happens in the next phase? What happens when they stop merely adapting to our cities and begin using their massive economic and predictive leverage to proactively redesign our physical world to better suit their own optimal fluid state?